This is the fourth and final notes on gas laws, so you definitely should have already seen the other three. We've looked at what gases are like. We've looked at the little gas laws, 4 of them, and now we're really going to get down to business. One phenomenon that we are trying to understand here is inflation. Inflation, like inflating a balloon, happens because of gas laws. If you put enough gas inside a balloon and there's enough pressure pushing out, then it forces the material to expand into the balloon shape. Later, we'll be dealing with this in the balloon lab, and I'll be mentioning that at the end of the notes. The ideal gas law is a beautiful equation that takes elements from all 4 of the gas laws we've looked at and crams them together into one of the most beautiful equations in all of chemistry. Remember, Boyle's law has pressure and volume, but what does it leave out? Temperature and moles. Charles's law has volume and temperature, but what does it leave out? It leaves out pressure and moles. Because Boyle's law leaves out temperature and has pressure in it, it's not very practical. Because Charles's law has temperature in it, but leaves out pressure, not very practical. Below we have the more practical equations, Gay-Lussac's law, which relates pressure and temperature, but remember that leaves out volume and moles. You can do that. You could keep volume a constant, and you can keep moles a constant. And then Avogadro's law is the most restricted one. It leaves out pressure and temperature, and of course they have to be at STP for it to even work. So because each one of these equations is limited or not practical in the real world, we need to take these relationships, tie them all together into one big equation. Each of the gas laws we've looked at so far just shows a relationship between 2 of the properties that you can measure for a gas. But in doing so, they often leave things out. For example, Boyle's law states that there's an inverse relationship between the pressure and the volume of a gas, but that only works if you leave out something. If you leave out temperature and moles. That means temperature and moles cannot change in the course of using Boyle's law. Between time 1 and time 2, they can't change. It doesn't matter exactly what they are, they just have to remain constant. So that's a problem. Very hard to do that. When you're changing the pressure, you're probably going to change the temperature. They're interlinked. They're like brothers. They're hard to separate from each other. Okay? Then Charles's law states that the relationship between the volume and the temperature of a gas is directly related, but that only works if you leave out pressure and moles. So if you leave out pressure, once again, it's not a terribly practical law. Gay-Lussac's law states that there's another direct relationship between pressure and temperature, but that only works if you leave out what? Volume and moles. So the volume has to remain constant for this equation to work, but that's something we can do with a tank. It doesn't leak. You'll keep the same moles. You can use Gay-Lussac's law in the real world. Avogadro's law is the most restrictive one because it leaves out, what does it leave out? It leaves out pressure and temperature. So pressure and temperature can't change for Avogadro's law to work. Not only that, they have to be at exact values. That's even more restricted than the other gas laws. But Avogadro's law, because it's so restricted, kind of works. It's fairly practical. We'll be doing an experiment later to check on it, okay, later on in this unit. So the problem is there's 4 measurable properties, and each one of these leaves a couple of them out. So what we need is one beautiful equation, one equation that ties all of these together. That is called the ideal gas law. The ideal gas law is a beautiful equation, one of the most beautiful ones in chemistry, that is fairly practical, and it ties all of these measurable properties together. Every chemical has its own unique boiling point. The boiling point is where something becomes a gas, from liquid to a gas. The boiling point usually depends on the molar mass of the chemical and on its polarity. The molar mass of a chemical determines the boiling point because if something is really, really lightweight, like a ping pong ball, it's much easier to knock it around, it goes flying. If something is heavier, like let's say a bowling ball, well, you hit it, it doesn't go so far. Remember, gases have to be bouncing around off each other, so you really have to get them moving. So it's much harder to move a more massive object. Way down at the bottom of the boiling points, way down by absolute zero, the coldest possible temperature, we see some very, very lightweight chemicals like helium and hydrogen. They both have boiling points very close to absolute zero. This scale is showing every line on here is 5 degrees Kelvin. Remember, absolute zero is negative 273 Celsius. So look where negative 250 Celsius is, just above the boiling point of hydrogen. So if you're colder than that, well, you might have liquid hydrogen. Otherwise, hydrogen is always going to be a gas, okay, until you get to plasma, of course. And then as you move up, you see neon. Well, neon is a little bit heavier than helium, so its boiling point is just a little bit higher, but still extremely cold. Look up this list above the negative 200 Celsius. Okay, that's actually about 77 Kelvin right there. That's the boiling point of nitrogen. What you're breathing right now is mostly nitrogen. And if you find liquid nitrogen, well, you know it's got to be really, really cold. And then just a little higher than that, we see fluorine, argon, oxygen. Then as we move up this list, I'm going to have it scroll through. Well, there goes methane and krypton, about getting close to negative 150 Celsius. You got xenon, a heavier noble gas, carbon dioxide, radon, hydrogen sulfide, chlorine, ammonia. Those are all below freezing of water. And then when we get to room temperature and above, we find a few more sort of lightweight molecules that boil a little bit above room temperature, like bromine. Notice where bromine boils, well, that's actually above any temperature we normally get on the surface of the Earth. So bromine is going to be a liquid under most circumstances on Earth. Okay? Look where water falls, way up at 100 degrees Celsius. Okay? That would be 373 Kelvin. So water really holds together even though it's kind of a lightweight molecule. Interesting that water does that because of its strong polarity. If you noticed, we passed a chemical that looked a lot like water down the list. That was hydrogen sulfide. Instead of an oxygen there, it has a sulfur there. Well, it's not quite as polar, so it boils at a much lower temperature. Anyway, the problem with this is every gas has a different boiling point. Well, we can't include all that in an equation. That would be a crazy equation. So, no gas perfectly obeys all of the gas laws under all conditions. The assumptions work pretty well, so keep that in mind. Gas laws are kind of an approximation. They won't always give you the exact result. Okay? So what we're really doing is we're pretending that we have ideal gases, like perfect little gases. And for perfect little gases, guess what? We pretend that they do not condense into a liquid. So no matter how cold you get, they would not condense into a liquid. That's like going the other way past the boiling point, going from the gas, cooling it down to make it a liquid. We ignore the fact that there even are liquids. So gas laws is kind of an imaginary world where every chemical just remains a gas at all conditions. So what you might find is that some of your results from gas law calculations seem very strange. Like maybe it's just a couple of degrees Kelvin and you think, well, most things would be liquid by then, if not solid by then. But we ignore that. So just keep in mind, these are not perfectly predictive. They're approximate. And we pretend that they're always gases at any range of temperatures. Okay, this is kind of like a legal disclaimer. Like after a medical commercial where they say, one of the symptoms may be lightheadedness. Do not take this if you are also taking this other medication. It's kind of like a disclaimer for gas laws. So just keep in mind that gas laws are predictive, but they're not perfect. Now we get to the big one, the mighty, mighty ideal gas law. The ideal gas law is represented by this equation, PV equals nRT. This is the way we normally write it. There's actually many different ways to write it, but this is the way I like to write it, and this is the normal way. Okay. The ideal gas law relates all of the measurable properties of gases. You can see pressure there, you can see volume there, you can see moles there, and you can see temperature, all packed into one beautiful equation. So those are our four measurable properties, our four variables. Oh, but wait, there's 5 letters here. So why are there 5 letters when there's only 4 measurable properties? Well, that's because R is something that's not a variable. Remember, we've seen something before that's not a variable, that's actually your friend. What would we call that? Something that doesn't change, that's always reliable. That is called a constant. So R is a proportionality constant. The value of R depends on the units you're using. I like to use the R that's at the bottom here. This is the R for liters, atmospheres, moles, and Kelvin. Look at the units of R. It's got the craziest units you've probably ever seen. The units of R are liters, atmosphere per mole, Kelvin. Don't even try to boggle your mind about what that even means. And R has a very, very low value, 0.0821. So you might imagine that that wouldn't have a big effect, because if you added that number to something, it wouldn't change it by much. It would just nudge it over slightly. But notice that we're not adding it, we're multiplying by it. So R gets thrown in there, and you multiply by R, it actually has a huge effect on the results. And the reason R is there is just to make those units work together. Those units were not designed for gas laws, so they don't naturally work together unless you plug in a little patch. R is like a little patch that makes it all work together. So notice that pressure and volume are in there, moles is in there, and temperature is in there. This is how they relate. Now the relationships are complicated. It's not simply direct or inverse now because of the way this equation is shown. It might be hard to see how this equation came out of the other gas laws. It might be easier if I show it in another form with condition 1 and condition 2. Looking at this form with condition 1 and condition 2, it might be easier to see how the other gas laws are put into this equation. We don't usually use the ideal gas law this way because lots of things can go wrong here. So we generally use the other form, but this helps you see how it was derived. Now it's P1 V1 over nRT1 equals P2 V2 over nRT2. So if you're in a situation where the moles isn't changing and R is a constant, well, by the way, R is always the same, so both of those R's are the same. We could really multiply both sides by nR and get rid of that. Now it's much easier to see where the ideal gas law came from, because you've got P1 V1 equals P2 V2 on top. That's Boyle's law. You've got V1 over T1 equals V2 over T2. That is Charles's law. And you got P1 over T1 equals P2 over V2. That's Gay-Lussac's law. The only one that you don't see here is Avogadro's law. And notice that I just multiplied both sides by n and got rid of that. But that's the reason that the n is there. It's much harder to see how that affects this. So anyway, this is another form of the ideal gas law. We don't usually use it in this form because many, many things can go wrong when you use it in this form. Generally, what we'll do if we have initial and final conditions, we'll just use the regular ideal gas law twice. Often what we solve for is moles, and then once we know what the moles are, we can just plug it into 2 equations. That is a more typical way to use it. That's sort of the way we'll be using it in some of our assignments. Here is an example of a typical ideal gas law problem. How many moles are in a 20-liter balloon at 10 degrees Celsius and 3 atmospheres? Now notice now we're putting in 3 quantities and we're solving for the 4th one. Remember, there are 4 variables in this equation. One of the letters is a constant, R is a constant, and the value of R is listed right there at the bottom. It's kind of small there. All right, so PV equals nRT, and we've got 20 liters. Well, where does that go? which of my variables is 20 liters? Oh yeah, that is my volume. So 20 liters goes right there. What about the 10 degrees Celsius? That is my temperature. Now, can we put 10 degrees Celsius into a gas law? You should know by now that no, we cannot, because that's not the total temperature. The total temperature is Kelvin. So how do I convert it to Kelvin? What do I add? 273. If you add 273 plus 10, 283. So that would be 283 Kelvin. That is the temperature I will put in. Never ever put Celsius into any gas law, including this one. And then 3 atmospheres. What is that? 3 atmospheres? Oh yeah, that's my pressure. So notice that we've got the pressure, we've got the volume, we've got the temperature, and we are asked for moles. So we already know that what we're solving for is N. Our answer should be the value of N, and guess what the unit is going to be? We already know. It's going to be moles. If you ever want to make sure you're using the correct units, look at the units of R. I know they're small here, but the units of R tell you which unit you have to use. So let's plug all those in to the ideal gas law equation. Notice my pressure is 3 atmospheres times 20 liters, which is my volume, equals N, we don't know N yet, times R, look at that crazy unit of R, times 283, that's the temperature in Kelvin. So what we do here is we will be canceling those units of R. The reason R has such crazy units is because it will leave you with the correct unit of your answer. It's a little difficult to juggle those crazy units, but we're going to try to do it at least in our first couple of assignments. We are going to juggle the units of R just to watch how they cancel. Notice we can multiply on the left side. 3 times 20, that's pretty easy. And we'll get a combined unit, atmosphere liters. That'll be 60 atmosphere liters. And then we can multiply on the right side, well, except for the N, we can multiply those two numbers together, those quantities. And only one thing is going to cancel there. It's going to be the Kelvin is going to cancel. So notice that we wind up with 60 atmosphere liters equals N times, turns out, 23.23 liter atmospheres per mole. Notice the Kelvin has now disappeared. You'll notice this happens with R. Each of the parts of it will disappear until only one is left. All right, so now the problem is I need to isolate my variable. My unknown variable is N. So that means I have to get rid of whatever is stuck to the N. The 23.23 is multiplied on. That means I have to divide both sides by it. If I divide both sides by 23.23, it'll disappear on the right side. It'll only be on the left side. So 60 atmosphere liters divided by 23.23 liter atmospheres per mole. Now notice if we divide atmosphere liters by liter atmospheres, those will both cancel. The tricky thing here though is what happens to that per mole. Well, we're dividing by per mole. So it's really on the denominator of the denominator, which actually, if you flip something over twice, it puts it right side up, and that puts moles back in the numerator. And we already knew that we were going to solve for moles. That's what N stands for, remember? So you know the unit has to be moles. Never give me some crazy unit like per mole just as a unit. That would be a strange answer. Now notice 60 divided by 23. Well, 60 divided by 20 would be 3. So it's going to be a number that's a little bit less than 3. And you divide it maybe on a calculator to get the exact number. And then you round off to the hundredths place generally. 2.58 moles. So that would be my answer. And then of course I would want to highlight it, okay, or put a box around it. So using the ideal gas law isn't too bad. We can't really cross multiply here because we don't have any numerators and denominators. We just basically solve for our unknown variable. And depending on which one you don't have information for, well, that's the one you're solving for. Just make sure that the other ones have those, here it's bigger now, the units of R. Just make sure the other ones, notice these units of R, make sure, see the K there? Well, that's why this has to be Kelvin. Notice the L there, well, that's why this has to be liters. And notice the atmosphere is there. That's why this has to be atmospheres. And then the only one that's left out of that is the moles. And that's because moles is our unknown variable. There are different units of R, or I should say there exist different units of R, different kinds of R, depending on if you're using kilopascals or even if you're using something like PSI. There's different R's. But I would like to stick with this R. In order to use this R, you need to have your pressures in atmospheres. So after we've had some practice with the ideal gas law, we will be doing a lab called the balloon lab. The balloon lab is a little bit tricky, so I just want to mention a few things about it right now to prepare you for that. So this is sort of in advance. We're talking about inflation, so we're going to do that. We're going to inflate a balloon. We're actually going to inflate 2 balloons, and I've made videos of the measurements that you're going to have to record, and we're going to be using those measurements to make calculations with the ideal gas law. Remember, a balloon would only inflate if the pressure inside is greater than the pressure outside. If the pressure outside was greater, the balloon would collapse. So the balloon lab is going to be using the ideal gas law to determine the pressure and the number of moles inside an inflated balloon. The problem with that is 2 unknown variables. The ideal gas law only works if you know all of them but one. So the tricky thing here is going to be, how can we figure out one of those 2 and then use it to determine the other? A little bit tricky. So what I've done, because this is such a tricky assignment, is I made it into kind of a cookie cutter lab. When you get the handout, you follow the instructions step by step, and it can lead you to the answer. It is a little bit tricky to follow all of the steps. We are going to be using thermometers to measure the temperature. Well, that's the easy part. Don't forget that most thermometers don't have Kelvin, so you're going to have to convert that, of course. To get the volume, we're going to have a cylindrical balloon, which we are going to use a little geometry. You might not have thought you were going to be using your geometry anytime soon, but here we go. To get the volume of a cylinder, we're going to use this equation. Some balloons are very round, so when we use a round balloon, we can use the formula for the volume of a sphere. This is one of the most beautiful equations in all of geometry. It only relies on one measurement to get the volume of the entire shape. It's kind of cool how that works. So we'll be using that, of course, to get the volume. So if we need to use the ideal gas law, well, we're going to need things. We're going to need things like pressure, volume, moles, and temperature. Oh wait, I already said that we were going to be calculating the pressure and the moles. So we're going to at least need to get the volume and the temperature. So to get the volume, we're going to use geometry. I talked about those equations. Down below, you see the equation for the volume of a cylinder with spherical ends. That's really the shape of what we call a twisty balloon, the kind you make little balloon animals out of. That's the formula for the volume of a twisty balloon. We add together the 2 equations. Because notice on the 2 ends, each end is like half of a sphere, of a ball. So that's what makes up the equation on the right. We can measure the mass of a balloon. That's going to help us get the moles, because there's something that relates mass to moles. What is that? What is that? Oh yeah, molar mass. So we are going to be using, of course, molar masses. You knew we weren't getting away from that. Just because we're done with stoichiometry, we're never going to get away from molar masses. We're never going to get away from molar masses. And then, of course, well, temperature is the easy one. Just bust out a thermometer. You can measure it pretty simply. And then, of course, never forget to convert to Kelvin. And what about R? Well, we always have R. As long as we use those units, we know R. So the next issue is, what is air made of? In order to do the balloon lab, we are going to need to think about what air is made of. Well, this is the simplified version. This is the one I believe it says on the handout. And if you need to resort to this, I will allow it, but this is kind of a little simple. So air, 79% nitrogen, 21% oxygen. So what would the molar mass of air be? Well, you know how to get the molar mass of nitrogen and oxygen, right? So what you would do is get the molar mass of each one of them, and then you would multiply it times its percentage. That would give you the contribution. Then you add the two contributions, and that's the molar mass of air. However, never forget the percentages are really out of 100. So if you want to get the number that a percentage really is, you've got to divide it by 100. In other words, 50%, 50 over 100, divide the 50 by 100, and you get 0.50. That's what 50% really means. It means half. When you picture air around you, you can picture it this way. Again, this is the simplified version. Mostly nitrogen and a little bit of oxygen, enough for us to breathe. But if you want to get real, well, actually, this is what I would prefer that you use, because air always has a little bit of water in it here on Earth, almost always, and it always has 1% of argon, a noble gas. We always forget about argon because it never does any work. It's the lazy element, so we usually sort of ignore it, but you're surrounded right now, you're breathing in 1% argon. So I prefer that you use this composition of air to get your molar mass. It'll be a little more accurate. Now, it's got more molar masses. You would do the same exact thing. You would multiply the molar mass of each chemical times its percentage in decimal form, and then you would add up the contributions to get the molar mass of air. You'll know that your answer is reasonable if it falls between the molar masses of each of the chemicals. It can't be larger than the largest one or smaller than the smallest one. Just like any average, averages always fall within the range of numbers that you use to calculate the average. If you want to picture the real composition of air, here's a little representation. Each one of these represents 1% of the air. So notice that there's only one argon. You can find the argon in there. And there's a couple of water molecules. This is kind of what is around you right now, kind of what you're breathing in. But that is not the same thing as what you're breathing out. So what if you were to inflate a balloon using your breath? What if you blew up a balloon, okay, using your mouth? Well, that would have a different composition, wouldn't it? That composition would be like this. Because notice that we've used some of the oxygen. That's the reason that we respire, the reason we breathe. So in the process of respiration, we use about 1/4 of the oxygen that went in. So if 20% went in, about 15% makes it back out. Some of it we have converted into carbon dioxide. Well, where did that carbon come from? That carbon came out of our bodies. So isn't it interesting that every time we breathe, we are losing some of the carbon in our bodies? It's not very much, okay? It's not very much with each breath, but over time it can be significant. And sometimes we also lose some of our water through respiration, but I'm not showing that here because it wouldn't be enough to register. These are rounded off percentages, by the way. So breath would have a different composition than regular air. So if you inflate a balloon, well then this is what's going to be inside it. If you inflate it with your mouth, this is what's going to be inside the balloon. So for the balloon, the spherical balloon, the party balloon that we are going to blow up with our mouth, at least in the video you're going to see, we are going to use this composition to get its molar mass. If you want to picture your breath, notice the only difference here is that some of the oxygen has now been replaced with carbon dioxide. And again, that carbon came out of you. In the process of respiration, we lose some of our carbon. So using the ideal gas law, we are going to be able to calculate first the number of moles in that balloon, which is a little tricky. I'll explain it in the video. And then using that, once we have 3 of the 4 variables and we have R, we can finally solve for the pressure inside that balloon, which is going to be the final answer. So I'll give you more information about this when we get to that assignment. So that is what we're going to be covering in gas laws. There's one little notation that I'll put on one of your assignments. If your pressure is given to you in kilopascals, my suggestion would be just convert it into atmospheres. The way to convert it into atmospheres is to divide by 101.3 kilopascals per atmosphere. So in other words, if you have 101.3 kilopascals, that is 1 atmosphere. If the number is greater than that, like let's say 120, well, you know that your answer is going to be more than 1 atmosphere, like maybe 1.19, I'm guessing. Or if your pressure is lower than 101.3 kilopascals, let's say like 80 kilopascals, well then your pressure in atmospheres is going to wind up being something very similar to like 0.79 atmospheres. You can sort of guess that because it's very close to 100, right? I could be a little off there, but you always divide the kilopascals by 101.3. I'll put that note on one of your assignments. Otherwise, this is what you need to know to do the gas law calculations. And good luck, and get ready for the balloon lab. Once you've had a little practice, we're going to do the balloon lab, and I think we'll also have time to do the dry ice lab.